Rob.
Okay. Oh,
So I'm excited.
okay.
But she said just come to this class and sort of fix it. So.
All right. I'm sorry. All right. So polynomial and complex zeros. What we're looking at today is solving polynomial inequalities and introducing odd and even functions. These are our goals for today. So just reviewing what we know from before. One of the important things from the lemmas from the fundamental theorem of algebra is this one. Given a polynomial function p of x, if p of a is equal to 0, then a is a 0 or a root of p of x. So if you put a value into a polynomial function and the result is 0, then that means that that value must be a root. From that, if a is a real number, then if x equals to a is a 0, we can always write a linear factor for p using that. So this is basically a couple of statements, you want to read them fairly carefully, which relate to your ideas and understandings from right all the way back to grade 9. When you solve quadratics, you factor them, and then you can see the roots inside the factors like this. Or you can set the factors equal to 0, and then you can solve and find the roots. So if you know a root, you can create a factor, and then you can take that factor out of the polynomial and get the diminished polynomial and slowly factor it. So if a linear factor is repeated multiple times, the corresponding 0 of the polynomial has a multiplicity of n. Typically, we know that a graph of a polynomial passes through the zeros of a graph. We can see this one passes through -1, which means we know that x plus 1 must be a factor. And we can see when we pass through this one that it's having a horizontal point of inflection. This one is going to have a horizontal point of inflection. So that means we must have an odd multiplicity. We could say that it's going to be 3. We're not certain of that from the information that we're given. We do know it's going to be of the form 2k plus 1. So an odd number where k is an integer. We can actually see it here in this one. We've got there. We have this. If we have a root like this one here, this tells us that we must have the factor x minus 4, and it has a multiplicity of 1. And we can see that it's going to be there. If we have a factor, if we have a root here at x equal to 3, it means we must have a factor x minus 3. Because we have a turning point, it has to have an even multiplicity. In this case, it's going to be 2. We can see it there. So that's the ideas of multiplicities and how the graph looks. Complex roots. So if we look at this graph here, what degree would we say it has? What's the minimum degree this graph could have? 2. It's going to be even, isn't it? And it has to be at least quadratic. But it doesn't have any roots. So how would it look? It wouldn't have any factors. Well, it's going to have complex roots then. So complex roots are given by, if we take the equation, we have this equation here, x plus 1 is equal to 0. If we wish to solve this equation, we would get x squared is equal to -1. Now, the problem with this equation is when you square any number, it's positive. So what squared will give a negative? We have to start by taking and considering plus and minus square roots of the number. Because it's quadratic, so we have to consider the positive and negative possibilities. And then we're left with having to square root -1. So what we do to solve this problem is we start by defining the letter I as being an imaginary number, such that I squared is equal to -1. This is how we define the imaginary number. We don't define the imaginary number as being the square root of -1. Some little problems that you can get from doing that. We start by defining I squared as being -1. This leads us to two possibilities for this. We will get x is equal to plus or minus I. And hopefully you've seen a little bit of complex number arithmetic last year. But I did speak to Miss Rayner this morning, and she said that some of you from the extended class haven't done it. So I would do a review of, I think I sent it to you in the Google Classroom. I sent you a review videos to prepare for today's lesson. If you haven't watched those videos before today's lesson, then you're going to be behind. All right, so what we're looking at today is the complex conjugate root theorem. Who has seen this one before? Okay, so the complex conjugate root theorem is quite simple. It says that if a plus bi is a root for a function, then the function must also have the complex conjugate as a root, a minus bi. Give a little bit of explanation here. So if we're looking at complex numbers, they're always of the form a plus bi. We have a complex number given here. What is the value of a in this? So this is 0 plus, what is the value of b? This is 0 plus 4i. What would the complex conjugate of that be? 0 minus 4i or simply minus 4i? Discuss with the people next to you, what is b? We'll just do one at a time for now. What is the complex conjugate of minus i? Discuss with the chap next to you. Make sure you remind me at the end of the class to put the attendance. Okay, so B. What is the complex conjugate of minus I? Let me take this check in front of me. I. C. What is the complex conjugate of minus 3i? Discuss with the people next to you. Do D as well. All right. C. Who can give me C? Somebody new. 2 plus 3i. And lastly, who can help me with D? I want to say Yusuf. So we're looking at this one. -4 minus 2i. Excellent. Sorry, can I close the curtains? Yes, please. Okay, one of the skills I would recommend, I sent you those videos for reviewing complex numbers when I realized some of the extended guys haven't got complex arithmetic. What you want, the skills that you want to solve, the skills that you want to practice is you should be able to solve equations of the type like this. So at this point, you should be able to solve this type of equation. I'll just do one as an example for you now. So to solve this equation, we can rearrange it to be x squared is equal to -16. This implies that x is equal to plus and minus 4i. So you need to practice. You'll find it on the videos, hopefully, that I sent. The other skill that you should practice would be to be able to do some arithmetic with these. So let's say, for instance, we have the complex conjugate 2 plus 3i, which is the complex conjugate of 2 minus 3i. You need to be able to expand expressions of this type. So it builds on FOIL. So just using FOIL, we would do 2 times 2, which gives us 4. We would do 2 times minus 3i, which would give us minus 6i. We would do 3i times 2, which would give plus 6i. And we would do, lastly, 3i times -3i. This is the tricky one. So this one will give us minus 9, and then we'll start with I squared, like this. Now, the great thing about the complex conjugate is that's always going to happen. That's the whole point of it. Now, from the definition, what is I squared equal to? So minus 9 times negative 1 will give us 4 plus 9. So this is equal to 13. A useful formula here for these type of expansions is if you have a plus bi multiplied by a minus bi, then the expansion is always going to be a squared plus b squared. Super simple. I would take a note of that formula. Okay. So the fundamental theorem of algebra says a polynomial of n degree has exactly n complex zeros, counting multiplicities. So when we talked about this the other day, we were asking how many real zeros does a polynomial have, and we said at most n. Now, when it comes to complex zero, it will have exactly n, because the roots could be complex or they could be purely real. Real numbers are considered complex. Real zeros are considered complex zeros, but complex zeros don't have to be real. They can be including an imaginary component. So we have the problem given here, the example. The graph of the polynomial function f of x is shown in the box. It is known that x minus I root 3 is a 0 of f. If f has a degree n, what is the least possible value of n? I'll give you 2 minutes to work with the people next to you. This is an exam-style question that you would have 2 minutes for. Have a go at this question now. Discuss and explain. Let's make it multiple choice.
Anyways.
Hello. Sorry.
So if the function,
Oh, it's a question. All right.
so if the function is equal to I square root of 3, the function is equal.
It's not.
Oh no, if the x is
The root.
the
Or the 0. The 0 is I root 3.
that's like if there if f has a degree n, because we don't know the degree, what is the least possible value of n?
That's the question. You've got the graph as well.
So it's negative I. Does that make sense?
Yeah, okay, let's see if I can use
Yeah, you got 4 choices. You have to pick one.
I can't just randomly guess because that's not fun.
I'm going to go through it in a second.
See if my estimations are really that bad.
Okay, 1 more minute.
This is turning point. It turns at minus 1. If it turns at minus 1, that means it's 0. Wait, is that an actual person? Or you just, that's what he said.
That's an actual thing. It should be learned now.
And if you just like this curve like this, so the x-axis is off. So turning point on the x-axis.
All right, let's stop there. Let's have a look. Let's have a look. Zinedine, go up to the board and explain the answer. Can we have quiet, please?
On the board.
Don't write on it, just explain. You point and I will write.
Okay, so we have x equals I root 3 as the root. So using the complex conjugate theorem, so it will be negative I root 3. Yeah. So that's two roots already. Then if we look at the graph, we can see that there's a 0 at 3. So we have x equals 3 as a root. Then over here we see there's a solution at -1. However, there's also a turning point. And if there's a turning point on the x-axis, then it's even degree. So it could have a multiplicity of 2, 4, 6, but we were asked to find the least possible value of n. So we could simply assume that it has a multiplicity of 2. So that's 1, 2, 3, 4, 5 solutions. So the answer is D. Yeah.
Yep. What else could we determine? Why do we know the degree is odd?
Because the function increases and decreases without bound.
The function increases and decreases without bound, so it must be an odd degree function. So 5. Thank you very much, guys. Excellent answer. If you fill my water, I'll be back. All right. This is our new topic for today, polynomial inequalities. Sorry, this is actually just a reminder because you're just reading a graph. It's the next page. So looking at this graph, where is the function equal to 0? Where is the function equal to 0? It's equal to 0 here, here, and here. So that would give us x equals -3, -1, and 3. Where is the function positive? Where is the function positive? The function's positive here and here. So this is going to give us some inequalities. So we are going to have -3 up to -1, union 3 to infinity. The last one is, where is the function non-positive? Why do I use the phrase non-positive here? Let me take that check.
We say non-positive because it says greater than, less than or equal to 0.
Less than or equal to. So we want non-positive values. That's these ones. So to give the interval for this one, it's going to start at -infinity and it's going to go up and include 3. So I use the square bracket. We're then going to include -1 and we're going to end at +3. So this is where the function is non-positive. Right, this is it. This is our goal for today, solving nonlinear inequalities. So in the homework, this is the most important area to focus on. This is the most important area to focus on. I'm going to do the first one for you. I'm just going to stop my video recording and then start a fresh one.